Hello everyone, my name is Jiahao Li. Today I would like to talk about an optimum days of scheduling in the IE514 timetable. This topic is mainly from Journal of Applied Mathematics and Decision Sciences. So first of all, what is 1421 timetable? It's a days of scheduling that has a 3-week or 21-day cycle. In every cycle, each employee is assigned one work stretch of 14 consecutive workdays and a break of 7 consecutive days off, which means each employee gets only one 7-day break instead of the usual 3 weekends off during the 3-week cycle. This schedule commonly used by some big companies to schedule employees in remote areas. Therefore, another reason of using this schedule is to reduce cost of transportation to remote work locations. The 1421 timetable is a restricted work schedule. It is only applicable to employees in remote work locations. Next, the objective of this kind of scheduling. Like any other days of scheduling, the primary purpose is to minimize the workforce size, which is the total number of employees assigned. A secondary objective is necessary here in order to reduce transportation cost, which is to minimize the number of employees actually assigned in each active pattern. Then all employees assigned to the same off-days pattern will be transported together, since these companies usually have private, for example, aircraft. Transportation cost depends on the number of flights, not on the number of employees on each flight. Therefore, total transportation cost is proportional to the number of active days of patterns. The 1421 days of scheduling problem is an integer problem. In this integer linear programming model, xj is the number of workers assigned to weekly days of pattern j. Coefficient epsilon is a constant that indicates small weight in objective function. Vj is a logic variable which counts for numbers of patterns. Then objective function is to minimize the number of workers and the number of active days of patterns. First constraints ensure that daily labor demands are satisfied for every day during the 3-week cycle. Ri is the minimum number of workers required on day I. Second constraint is necessary here to ensure that Vj is equal to 1 if xj is possible. And if xj equals to 0, then there is no workers in pattern j and Vj is 0. If we expand these constraints, we will actually have 42 of them with 42 integer variables. Therefore, it's necessary to develop the model. One way is to temporarily ignore the coefficient epsilon since it's small-weighted. For example, if we have a days of matrix like this, then we will find 2 of the 3 variables xk, xk plus 7, xk plus 14 are always present in each labor demand constraint. Therefore, we obtain aik plus aik plus 7 plus aik plus 14 has to be 2, which leads to xk plus 7 plus sk plus 14 equals to 3/2 of Ri. Given that the labor demand constraint is at least equal to Rmax, then Ri actually equals to Rmax. Finally, we will obtain this equation. Another approach of doing this is to find the duality of LP model, which we learned before from optimization class. Basically, its constraints becomes 2 variables and minimize convert to maximize. Then we will obtain a developed model as following. W here is the workforce size, which is the number of workers assigned to all 21 days of patterns. It is an efficient optimum solution technique that has been presented for scheduling employees using a real-life days of schedule. However, it has some restrictions and mainly used for scheduling employees in remote work location where transportation cost is high. The efficient method utilizes the dual solution and primal dual relationships to eliminate the need of using integer programming for this particular scheduling problem. Therefore, the solution method can be simple enough to use manual calculations. That's all my presentation today. Thank you for listening.